All right, Year 12, I'm about to go over multiple roots, which is exercise 5B from Patel in polynomials. And we've already done this stuff here. This is the syllabus document and the dot points. And we look at 7.1, integer roots of polynomials with integer coefficients. And we've just been using the remainder and factor theorem to go through these. Look at the dot point, prove that if a polynomial has integer coefficients and if a is an integer root, then a is the divisor of the constant term, which just is the remainder theorem. And the second dot point, test a given polynomial with integer coefficients for possible integer roots. So that's pretty easy. We know about that. That's a remainder and factor theorem, and we know how to test them by substituting in p of 1 or p of 2 or p of 3 and using that. What we need to look at now, though, is multiple roots. Let's have a look at the dot points. The student is able to define a multiple root of polynomial and to prove if p of x equals x minus a r times s of x, where r is greater than 1 and s of a is not equal to 0, that means it's not a null polynomial, then p dash of x has a root of multiplicity, and we're going to prove that in a minute. It's quite easy to prove. And solve simple problems involving multiple roots. This is not that hard, exercise 5B, and when you see this, you will understand that it won't take you much time at all. So, here's our theorem. If x minus a is a multiple root, or a multiple factor of p of x, then it's also a factor of p dash of x. Now, you've got to learn this, but it's quite an obvious thing. But let's do the proof anyway. So, our proof. If, we've got some 3 dots there, if x minus a is a multiple factor of some polynomial, p of x, then x minus a is also a factor of p dash of x. Okay, so now we're going to prove that. So let's take p of x, and we know that p of x is, or x minus a is a factor. So, and it's a multiple factor. Now we don't know, so we'll just put n up there. Could be a factor of 2, could be a double root, could be a triple root, could be any number. So p of x equals that times q of x, where q of x is just another polynomial. And there's no remainder. There's no r of x because it's a factor. That's what we're told. That's our statement. If x minus a is a multiple factor of p of x. Okay, well, how do we prove that it's going to be a factor of p dash of x? Well, p dash of x, well, what we've got here, we've got two functions. So we're just going to use product rule. And the product rule is the first times the derivative of the second, just q dash of x, plus the second, q of x, times the derivative of the first. Well, on that first, I'll use a fat finger rule. I'll bring the n down. I'll have x minus a, and I'll take 1 away from the top. And because it's linear in there, I'm just going to multiply by 1, by the derivative of what's inside. I can write it, but I don't need to. Now, what have we got here? Well, let's factorise the x minus a n minus 1. I shouldn't have to show that this bit here is x minus a to the n minus 1 times x minus a. You should realise that. So I'll take x minus a to the n minus 1, and I'll put a big set of brackets. Now, what am I left with? I'm left with an x minus a. Please make sure that you understand that that times that gives you what's underlined in red. Okay, and I've got a q dash of x. Now, if I take x minus a to the n minus 1 out of there, I'm left with an n and a q of x. So again, there's no remainder here because this is just another polynomial. This is another polynomial. And we'll just call it w of x. Doesn't matter what letter we use. So now we've got p dash of x equals x minus a to the n minus 1 w of x. And again, there's no remainder. Hence, x minus a is a factor of p dash of x. Now, it's pretty obvious. Well, you understand that. And this is proved in Patel on page 150. And Patel goes on to say, well, let's have a look at this. If p of x equals x minus 2 squared, x squared plus 5x plus 10, well, x equals 2 is a double root. Well, what about if p of x equals x minus, I don't know, we're going to use a different one to Patel. Patel uses x minus 2 again. I'm going to use x plus 3 all cubed times x squared plus 4. Well, x equals negative 3 is a triple root. And let's have a look at that. If x equals a is a triple root of p of x, it is a double root of p dash of x and a root of p double dash of x. And that's pretty obvious. And Patel goes on to say that. So you can keep going down. Like if it was a quadruple root, it'd be a quadruple root of p of x, a triple root of p dash of x, a double root of p double dash of x, and a root of p triple dash of x. And we've already gone through all this, and we know, and now it should make sense for you to understand that we know a double root is a TP and a triple root is a PI. Okay, so let's go on with a couple of questions. Now, I'm going to do one that's very similar to the example one that Patel does on page 171. He does an example where he says, show that such is a certain root is a multiplicity, is a multiple root of a polynomial, and you just do differentiation to find it. So I'm going to just do, this is similar to example 7. So here's an example question. And it basically says, solve x cubed minus 3x plus 2 equals 0, which we don't know how to do. Remember, when we started this whole extension 2 topic off and we kicked off with complex numbers, they all were developed for solving cubic equations. So Cardano and all those characters, they solved cubic equations and they kept it all secret. Remember that? So there are formulas for this, but we don't need them because we can play with integer solutions to these. Now, they won't always be integer solutions and they might be complex solutions. But in this case, they're telling us to solve this, but they give us a little bit of extra information and they say, given it has a double root. And immediately you go, no worries. I'm going to say P of x is x cubed minus 3x plus 2. And I'm going to differentiate it. P dash of x equals 3x squared minus 3. Now, because I know it's a double root, there's a double root in that first P of x, I'm going to put this equal to 0 and find the solutions. So I'm going to let P dash of x equals 0. So I get 3x squared minus 3 equals 0. 3x squared equals 3. X squared equals 1. So x equals plus or minus 1. I could have just factorized. P dash of x and written it as 3 x squared minus 1 and gone, oh well, 3 x plus 1 x minus 1. But I can do it this way as well, and I go, well, x minus 1 or x plus 1 is a double root, because they're the only roots of the derivative, and I've been told that one of them, or that there is a double root in the original equation. So one of these, all right, is a double root. So note, only one is a double root. Well, how do I find out which one? Easy, I just use the factor theorem. So I always go for P of 1 first, which is this one, when x equals 1. And I go, oh, P of 1 equals, so what's the first equation? X cubed minus 3x plus 2. So 1 cubed minus 3 times 1 plus 2. Oh, that equals 0. So x minus 1 is the double root. I could go on and find P of minus 1. I don't need to, but I'll get minus 1 cubed minus 3 times minus 1 plus 2, which equals minus 1 plus 3 plus 2, which equals 4, which is not a factor of the original cubic equation. So therefore, P of x equals x minus 1 squared, we know it's a double root, times q of x. And because this is a cubic, well, we know that that's a single equation. How would I find out what that is? Well, I'm just going to let q of x equal x minus alpha, where alpha is the third root. Okay, so now I've got a choice. I could do long division. I could do x minus 1 into the original equation and then do x minus 1 into the next equation. But there is an easier way to do this. So let's see. I know p of x is x minus 1 squared times x minus this other root. Okay, well, let's sub x equals 0. And p of 0 gives me 0 minus 1 squared, 0 minus alpha. That'll give me 1 times negative alpha, which is negative alpha. But because I know the original equation, but p of 0 equals 0 cubed minus 3 times 0 plus 2, which equals 2. Therefore, or thus, alpha, negative alpha, must equal 2. Therefore, alpha equals negative 2. And p of x equals x minus 1 all squared, x minus negative 2, which is x minus 1 all squared, x plus 2, which I could then expand out and get the original equation just to double check it. But what does this mean? Okay, let's have a look at this even a little bit further. So remember we had to solve it. We've now solved it. So the roots are x equals 1 and x equals minus 2. And now for a little bit more joy, let's have a look at what this is. So we have negative 2 and 1. We know that the polynomial p of x is x cubed minus 3x plus 2. So we know it's going through 2 up here. We know that this is a double root. We know it's a positive cubic. And if you remember, when we differentiated it, the other option of the second derivative was at minus 1. So this cubic comes up, turns around, comes down, and goes up like that, which should make curve sketching for you guys so much easier. Now, what I want you to do after you've watched this video is I want you to go and do these questions. Exercise 5B, questions 1, 4, 5, 6A, 7A, 8A, 8C, 8F, and 8I. All right, good luck.